Hey everybody, welcome to Graphing Basic Trig Functions. In this video today, what we're going to do is we're just going to look at, it's called basic trig functions because we're just going to look at the base graph. We're going to look at all 6 trig functions: sine, cosine, tangent, secant, cosecant, and cotangent. But we're just going to look at those. No like 2 sine x plus 2 pi or anything. It's just going to be sine of x. It's just going to be cosine of x, okay? Because we need to have a good notion of what these base graphs look like before we try to do things like multiply them, divide them, add things into their periods, adjust their amplitudes, things like that. So this video is only going to deal with base graphs. And this is what we're going to do. So for each one of these graphs, we're going to first create a table of values from 0 to 2 pi. And this is going to be for we're going to go through every single trig function. So we're going to do 6 of these. And then we're going to plot it on the xy plane. So we're going to plot the points. And then once we have our graph on the xy plane, we'll get to see the shape, which is important. And then we'll find the domain, range, period, and amplitude. Now these 2 words are new for us, of each graph. At the end of everything, we'll have this nice table of properties for all of the 6 trig functions. At that point, you're probably going to want to pause and take that down because that's going to be kind of the conclusion of everything we've seen thus far. So before we start, though, let's define what these new words period and amplitude mean. So what does period mean? So the technical definition, the length of the smallest segment of the x-axis that it takes for a graph to go through one complete cycle is called the period of the graph, or the equation it came from. In symbols, if p is the smallest positive number for which f of x plus p equals f of x, for all x, we say the period of f of x is p. Now, all that means is the period is just the length, so the length on the x-axis. So the length on the x-axis that it takes for the graph to repeat itself. So all these trig functions will repeat themselves infinitely on left and right from negative infinity to positive infinity. So what this period is, it's just, hey, how long is one of these cycles? How long does it take for this graph to repeat itself again? That's what period is. And then amplitude. So what is amplitude? The greatest value, y, is capital M, and the least value is lowercase m, and the amplitude of the graph is defined to be capital A. 1/2 of the difference, the absolute value of the difference, capital M minus little m. All this means is take the highest point on the graph, take the lowest point on the graph, and cut it in half. Okay, so the amplitude is not just the highest part on the graph. It's also not the complete distance between the highest and lowest. It's half. Okay, so look at the highest point on the graph, look at the lowest point on the graph, half that. That's what we're going to call amplitude. Okay. Now, let's go get some graphs and let's do our domain, range, period, and amplitude of them. Okay, so here's where we're going to graph all of our functions. And the first function we're going to start off with is sine. So let's make a table of values from 0 to 2 pi. And we're using the Desmos program, so it is going to spit us out numbers in decimal form and not in our exact form. But we will still be able to see on the graph where those are. So for sine of 0 is 0. And then we're going to go in increments of pi over 2. So pi over 2, then pi, and 3 pi over 2, and then 2 pi. And you can see here on the right side, let me move my graph over a little bit. Here is what sine is going to look like from 0 to 2 pi. And you can see it's kind of an up and down wave, which is why we call a sine wave. So if we look at the whole sine graph, it looks like this. And this is what's going on infinitely left and infinitely right. And you can see that it is repeating, right? Like if we look, right, a cycle of our graph starts here. We go up, we go back to 0, but then we go down, and then we go back to 0. Here is the cycle length here. And this is what we would call the period. So how long does it take for this graph to repeat itself again? Well, from 0 to 2 pi, right? Not from 0 to pi, because then we dip negative again, right? These values don't start repeating themselves until I get to 2 pi. We can see that visually. So the period here would be 2 pi. How long does the graph take to repeat itself? Well, every 2 pi, this graph is going to look exactly the same. Now, what about amplitude? So amplitude is 1/2 of the tallest point. Well, the tallest point is here at +1. The lowest point is here at -1. So the absolute value of 1 minus -1. So add these together, that'd be 2. 1/2 of 2 is 1. So our amplitude of our graph is 1. Our domain here, as we see, there's no breaks, there's no asymptotes. So the domain would be all real numbers. And the range, right, the lowest point on the graph to the highest point, the lowest point is -1, the highest point is 1. So y, and it hits, is less than or equal to 1, but greater than or equal to -1. Okay, so that's our sine graph. And notice sine starts and ends at 0. Sine starts and ends at 0. That's the most important thing. For the periods to repeat, we start and end at 0. That's for sine. All right, let's go to cosine. So thank you, sine. Thank you, sine. Let's cruise over to cosine and do the same thing. So let's make our table of values and see what it looks like. So let's go 0, then let's go pi over 2, then let's go pi, then let's go 3 pi over 2, and then 2 pi again. So look at, we see our cosine looks a little bit different, where our sine started at 0 or 0, boop, 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 like that. Cosine almost looks like a curvy V, right? And if we complete all the dots from negative infinity to positive infinity, there's our cosine. Okay, notice this is a little bit different than sine because we start at 1. Cosine starts at 1, sine starts at 0. So let's see what our period is. So here's the start, and how long does it take for it to repeat all the way back up to here? And this is going to be 2 pi, so 0 and 2 pi. So our period is equal to 2 pi, because every 2 pi it repeats itself again. Like, look, here's another repeating section right here. Every one of these sections is a carbon copy of the other one. So our period is 2 pi. Our amplitude is 1/2 of the tallest point minus the lowest point. The highest point here is 1. The lowest point here is -1. The difference of these two and cut in half is again going to be 1. Tallest point minus the smallest point, the difference, the absolute value of that difference is going to be 2. 1/2 of 2 is 1. All right, domain. There's no breaks, there's no asymptotes, so this is going to be all reals. And the range. Range, remember, is the lowest point to the highest point. Well, my lowest point is -1, and my highest point again is 1. So everything about sine and cosine looks about the same. What's different here is the shape, right? My y-intercept is 1 versus my y-intercept of sine was 0. So keep that in mind. Okay, so they almost look like opposites. And if we put them actually on the same graph, so this is the cosine, this is the sine. So cosine, sine, look at, they kind of alternate, right? Which is pretty cool. So thank you, cosine. Let's move on to tangent. You're going to see the table of all of these properties at the end, so don't worry about if you're trying to copy them down feverishly. There'll be a nice table at the end that'll have all these properties. So let's see tangent. So cosine and sine were pretty similar. Let's see if tangent is going to play nice too. Pi, and then we got 3 pi over 2, and then we got 2 pi, right? Oh, tangent's looking pretty weird when I put this same chart in, right? Why? Because at pi over 2, it's undefined, and 3 pi over 2, it's undefined. So that's pretty weird. So let's see what tangent looks like. So if I were to connect all these dots, if I were to put in probably every pi over 6, this would have looked a lot better. Why? Because every multiple of pi over 2, tangent is undefined. Why? Because tangent is slope. Think about your unit circle. Where is pi over 2 on the unit circle? Where's 3 pi over 2 on the unit circle? Those are the vertical lines. Slope of a vertical line is undefined. Tangent at these points then is undefined. And notice we have an asymptote here at pi over 2. So this is the asymptote that I put in. So if every pi over 2, we have a problem. So pi over 2, we have a problem. 3 pi over 2, we have a problem. And if you keep adding multiples of pi with with pi over 2 plus multiples of pi, we will create an asymptote. So what does this mean about tangent then? So first off, what's the period of tangent? Well, the period of tangent, let's see, how long does it take to repeat itself? So this is pi over 2 right here. And this right here is negative pi over 2. So if I were to draw another asymptote, so from negative pi over 2 to pi over 2, it repeats, right? We got a squiggle, and then we got a squiggle, and then a squiggle, and a squiggle. So each one of these squiggles, from negative pi over 2 to pi over 2, how long is that? Well, that's a length of exactly pi. So my period here is pi. So every pi amount, I'm going to get a perfect copy of one of these squiggles, right? From here to here is pi. From here to here is pi. From here to here is pi. Pi, pi, pi. These squiggles repeat every pi length. So the period here is pi. The amplitude, so if I take the lowest point, which is negative infinity, the highest point, which is positive infinity, cut it in half, it's still infinite. Amplitude, I actually don't have an amplitude for this. Okay, why? Because it goes off forever vertically up, and it goes off forever vertically down too. So amplitude, I don't have one. Or some people will say that it's infinite. Okay, domain. Domain is everything except for these pi over 2's, right? Pi over 2 is a problem. 3 pi over 2 is a problem. So think a half is a problem, 3 halves is a problem, 5 halves is going to be a problem, 7 halves is going to be a problem. So the domain is all x except, so all x cannot equal to any multiple of pi over 2, and then we say plus k pi. In other words, anytime pi over 2 is added with another multiple of pi. So plus pi would be 3 pi over 2. Plus 2 pi would be 5 pi over 2. Plus 3 pi would be 7 pi over 2, and so on. Every one of these like multiples of pi over 2's, we got a problem. So domain is everybody except for these guys, right? Because these are where our asymptotes come in. Our range, well, how far down do we go? Negative infinity. How far up do we go? Positive infinities. Do we break at any point? No, we don't. So our range is actually all reals here. And again, you guys will see a really nice chart of this at the end of the video. All right, so that's the shape of tangent. And no, tangent has asymptotes at pi over 2 multiples. So tangent doesn't like pi over 2's. And it looks like this vertical squiggle. All right, let's get into our reciprocal graphs. So that was all of our main ones. That was our sine, cosine, and tangent. So now let's look at our reciprocals. So if we look at our secant graph, whose reciprocal is secant? Well, secant is cosine's reciprocal, which means if we took all of the values in our cosine graph, let me get rid of this asymptote. If we took all of our values in our cosine graph and we just flipped them over, we would get our secant graph. So what I mean by that is we have 0, pi over 2, we have pi, we have 3 pi over 2, and we have 2 pi. So it looks like we also have the same problem at multiples of pi over 2 for secant. And let's look at what the secant graph looks like. It looks like this. Now, if you want to see something really cool, the secant graph and the cosine, right? Secant and cosine are reciprocals. Look at this. If we put the cosine graph back on, boom, right? So basically all the space not covered by secant, like, is covered by cosine. All the space not covered by cosine is like covered by secant. So this is always really cool to put the reciprocal graphs on each other. So what's the deal with secant then? So this is secant's graph. So where are the asymptotes at secant graphs? Well, it looks like every pi over 2, we have a problem again. And every pi over 2, so this is the asymptote. Every pi over 2, we do have a problem. So we have kind of the tangent situation. Pi over 2, we have a problem. 3 pi over 2, we have a problem. 5 pi over 2, we have a problem. 7 pi over 2, we have a problem. Kind of every pi over 2 plus multiples of pi, we have a problem. So how long is one of these periods? Let's see. Well, the graph contains one of these upward U's and one of these downward U's. So let's see. Here's the end of the upward U. Here's the end of the downward U. So this is also an asymptote over here. So this asymptote here is at positive. Put this back up so we can see our table. There it is. So this asymptote here is at positive pi over 2. We have another one here. This would be negative pi over 2. But the graph doesn't repeat every pi over every pi, right? This is the length of pi. If it did, we would only have a collection of upward U's, but we don't. We have upward U's and downward U's. So this period contains the downward U and the upward U. This is negative 3 pi over 2. So how long is this period then? Well, it takes me from negative 3 pi over 2 all the way to pi over 2 to repeat. That's negative 3 halves to positive a half. How long is that in total? Well, it actually does take me the entire 2 pi to repeat this graph, which kind of makes sense, right? Because cosine's period is 2 pi also. So that's an interesting coincidence. Amplitude, same thing, because we blow all the way up to positive infinity and down to negative infinity. Our amplitude, you can either think of it as infinite or non-existent. What else do we got? Domain. Domain, we can plug in everything except for these multiples of pi over 2 again, right? So our domain is all x except for pi over 2's plus k pi's. In other words, all pi over 2's and multiples of pi added to that, right? Negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. All of those, no-nos, we're going to cause asymptotes there. Range, here's where it gets interesting. Well, I go all the way down to negative infinity, right? But I have a gap. I have a gap between here and here, right? So this is 1. Sorry, this is negative 1. This is positive 1, right? There's a gap between negative 1 and positive 1. Isn't it interesting that cosine only exists between negative 1 and positive 1? Interesting. So our range then is from negative infinity, and I'm going to put this in interval notation, from negative infinity to negative 1, and we actually hit union 1 to positive infinity. Infinities always get the curve. In other words, vertically, we cover all the space except for the space between negative 1 and 1, right? There's a gap here. So that will be the range. Again, we'll see a very, very nice table of all this, and you guys won't have to pick through my chicken scratch. All right, let's look at our last two. So our last two are going to be cosecant and cotangent. We're going to do the cos last. Let me get rid of my asymptote. So cosecant is the opposite of sine. So let's look what the opposite of sine looks like. 0, pi over 2, pi, 3 pi over 2, and 2 pi. So there's my points. Oh, again, I have things that are undefined. But this time, my undefined, sorry, I guess I'm doing cotangent. I'm going to do cotangent first. And then I'll back up to see cosecant. So cotangent. At this time, I'm undefined at 0, I'm undefined at pi, and I'm undefined at 2 pi. So I'm undefined at all multiples of pi. So here's my cotangent graph. This is the reciprocal of my tangent graph. There's tangent, cotangent, tangent, cotangent, tangent, right? Reciprocal. See how cool that is? So my cotangent graph, what are my properties of my cotangent graph? Well, how long do one of these periods take to repeat? Well, here's the mark of 1, and here's the mark of the other one. How long are these? Every one of these periods are pi, right? Which is the same period that tangent had. So it's interesting that these have the same amplitude. We don't have one, or you can call it infinity because it goes all the way up forever and all the way down forever. We're not tamped off either way. Domain, everybody comes except for anybody who's a multiple of pi, right? Any multiples of pi, 0 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, all the pi's. No pi's allowed, right? So all x's except for x's such that they're multiples. K just means multiples, multiples of pi. All x's are cool unless you're a multiple of pi. If you're a multiple of pi, no thank you. We don't want you. You can't sit here. You're not allowed. Okay, but everybody else, you're cool. And then range. Range, we go all the way down to negative infinity. We go all the way up to positive infinity, and there's no breaks in between. So this range is all reals. Notice the tangent range was also all reals as well. So this is the shape of cotangent. It's just literally what looks like kind of the reflection of the tangent. All right, last guy is cosecant. Oops. Cosecant. Thank you, cotangent. Let's now look at cosecant. The cosecant is opposite of sine. 0 pi over 2 pi, 3 pi over 2, and 2 pi. All right, we also have some undefined. So let's see what the reciprocal of sine looks like. Hey, this looks pretty familiar, right? Who else did we see that had these u's going on? Well, who else had u's going on? Well, secant has u's going on. So secant and cosecant have u's going on, right? But notice these are the same, except they're kind of shifted horizontally, left or right. Who else looked the same, just shifted horizontally left and right? Well, sine and cosine did, right? So it's no coincidence that the reciprocal graphs also just look like shifts of each other as well. So cosecant now at 0 is undefined, and we have asymptotes every pi, right? So you guys are starting to catch on now. So from here to here is one of the periods. That's negative pi. That's positive pi. So we have a downward use and an upward use repeating every period of how long is it from negative pi to pi? Well, it's 2 pi. Interesting enough, it was the same period for sine and cosine. Notice that. Amplitude, again, we don't have one because we go up forever and we go down forever. Domain is everybody except, right, because we have some undefines. Domain is, oops, and I'm doing that for cotangent, which is not what I want. Domain is everybody except, there's my cosecant graph. Domain is everybody except for multiples of pi. 0 pi, 2 pi, 3 pi, 4 pi, 5 pi, 87 pi, no thank you. So x is everybody except for multiples of pi. K means multiples of pi. Range is everybody except for, right, we have a vertical space between here and here. Between -1 and 1, there's blank space. The graph does not touch a y value of -1 to 1 at all. So the range goes from negative infinity up until -1, but we include it. And then it goes from 1 up to infinity. But this just means, hey, there's a blank space in our graph vertically from -1 to 1. So that's why the range looks like this. So the big takeaway here is kind of like shapes, right? Cosecant and secant look like up and down U's. Tangent and cotangent, get rid of this asymptote. Tangent and cotangent, so there's cotangent, here's tangent, look like vertical squiggles. All right, I know that's not mathematical, but tangent and cotangent look like vertical squiggles. Cosecant and secant, up and down U's. Tangent and cotangent look like vertical squiggles. And then sine and cosine look like shifted waves. Sine and cosine, shifted waves. Secant, cosecant, shifted U's. Tangent, cotangent, opposite looking vertical squiggles. Okay, so that is the main point, is kind of seeing, hey, what's the shape of all of these base graphs? And now let's look at our conclusion for these tables of values. So here's the conclusion rolled up in one nice chart. So our functions sine and cosine had the same properties. They're all real numbers. The range, amplitude, and period were all the same. And then here is everything laid out for you, not a lot nicer than what I had in my chicken scratch. It gives you the domain, range, amplitude, and period for all 6 of the trig functions. So right here might be a good time to pause, take this down, this nice organized data of all of it. Also, my suggestion would be next to each one of these, you draw kind of the shape of the graph, right? Wave, wave, vertical squiggle, up and down U's, up and down U's. Or sorry, vertical squiggles, up and down U's, up and down U's. I read that as cosecant. Okay, so it's probably a good idea to have the shape along with these guys, and then you'll have a great cheat sheet of, hey, this is all my base graphs. Here's my shape. Here's my function, domain, range, amplitude, and period. And that's a great jumping off point for next when we go into transformations. So thank you guys for watching. I'll see you guys next time. And as always, if you have any questions, please don't hesitate to ask.